So today we're going to be looking at a couple of challenging circuit problems. We're going to be doing 3 specific problems, and they'll have something to do with resistors, capacitors, diodes, and a combination of those. And we're going to understand exactly how that combination affects the circuit behavior for each of those 3 problems. So without further ado, let's get into problem number 1. This problem number 1, we have a mixed circuit with a capacitor discharge. Looks like we had a 12 microfarad capacitor, which has already plus 10 volts across that capacitor, and we have a 3 kilo ohm resistor connected to that capacitor. Looks like there's some sort of discharge current going on within the circuit, and we need to find how much voltage remains after 6 milliseconds within this discharge circuit. So right away, my brain goes to finding some sort of time constant. A time constant is the rate of discharge dependent on how much voltage, how much current, and how much resistance is actually within this entire circuit. So we can solve this problem pretty quickly in a couple of steps. Let's look at step number 1, which is going to be find the time constant, as I mentioned. And that time constant is going to be something called tau. Tau is equal to the resistance times the capacitance. Pretty simple equation. Therefore, 12 microfarads multiplied by 3 kilo ohms is going to give us a value of 0.036 seconds. This is the rate of discharge. Step number 2, we can actually find the voltage. The voltage equation, voltage using the equation we're going to use is equal to V equals V naught times e to the minus t over tau. In this case, we already have a value of t, we have a value of tau, and we have a value of V naught, which is going to be the initial voltage on the capacitor being 10 volts. Therefore, let's quickly analyze this, is equal to 10 multiplied by e to the minus 0.006 over 0.036. This is the equation we're going to solve to find the final voltage after these 6 milliseconds. Therefore, if we plug into calculator, the final voltage, V, is going to be equal to 8.46 volts. That is the final voltage after 6 milliseconds, given this setup of 3 kilo ohms with a 12 microfarad capacitor. So pretty straightforward question. Really, all we need to understand is what this equation is. And the main equation that we use in this case, just to reiterate, is going to be V equals V naught e to the minus t over tau. This is the main equation we're going to use for these discharge capacitor type of questions. Let's move on to question number 2. Question number 2 is a little bit of an interesting question because it has a diode, it has 2 diodes specifically, with a 1 kilo ohm resistor, and don't forget that 5 volt battery supply as well. What is the current in the circuit? So with diodes, it's always very important that they have to be forward biased, meaning that suppose these diodes, I just write it over here, suppose these diodes were facing the wrong direction. They were backwards. Diodes always have a polarity to them. In this case, what I've drawn here, this is known as reverse bias. And this will mean that this circuit will not conduct any type of current. So there won't be any current in the circuit, especially if we have this type of reverse bias setup. However, in this case, what we have is a forward bias circuit because a capacitor acts in this sort of way and is able to conduct with a 0.7 volt drop across both terminals of the diode. We can pretty easily calculate the currents within the circuit. So this should be a pretty easy 2 or 3 step problem, in my opinion. So let's look at step number 1, which is going to be the total diode voltage drop. that is a pretty easy calculation that we can do. The diode is going to be equal to 0.7 plus 0.7, since they're two diodes, equals 1.4 volts. This is the voltage drop, meaning this voltage drop right here is 1.4 volts. 0.7 volts plus 0.7 volts is 1.4 volts. Now, how much voltage is left across the singular resistor is what's step number 2. Resistor voltage. In this case, we had VR is going to be equal to, so we have our 5 volts. We always start with that. So 5 volts minus the total combined voltage drop across both of those diodes. We already calculated that to be 1.4 volts. And that is going to be an answer of 3.6 volts. Again, very easy calculation. And then finally, it looks like we have voltages, we have a current. Now, all we need to do is just use Ohm's law in this case. Step number 3, Ohm's law. In this case, we solve Ohm's law for the current, since we're asked for the current in the question. So I equals V over R. In this case, the voltage across the capacitor, or voltage across the resistor, will be the voltage across the resistor will be 3.6 volts over 1,000 ohms, meaning that our final answer will be 3.6 milliamps of current that totally flows through this resistor, or through this entire current. So what is our main takeaway from our question here? Our main takeaway is that this forward bias versus reverse bias of these diodes is going to be very, very important. We always have to look at the direction that the diodes are always facing to make sure whether or not there even is current, or whether or not those diodes are going to be conducting in the first place. So diodes are very important. They're used all the time in protection circuits, specifically for power applications. And we'll cover those in some subsequent videos. Finally, let's go to problem number 3. So problem number 3 is a little bit more of a complicated circuit here, looks like. We have a 24 volt battery connected to 2 resistors. We have a 4 ohm resistor R1, we have an 8 ohm resistor R2, and we have a 12 microfarad capacitor that's in parallel with this 8 ohm resistor. What is the initial current the moment that the switch right here, let's highlight our little switch, is closed? So this question is really drawing on the fact of how a capacitor really acts within this transient response. What we need to know, and specifically the principle that we're going to use, let's highlight capacitor behavior. Suppose we have a switch in this case, and that switch is currently closed. That switch is currently open. There's no voltage on that capacitor. At t equals 0, the capacitor acts as a short circuit. However, if we extend that time all the way to t equals infinity, that is going to be an open circuit. Therefore, we can use these principles to answer our actual question. In this case, we know the instant that switch is closed, this capacitor right here is going to act as a short circuit, meaning that we can pretty much replace that with a wire. Therefore, since all current takes the path of least resistance, this 8 ohm resistor is essentially gone. So again, this turns into a quick one-step equation, one-step problem. Step number 1, we can easily use Ohm's law to solve this question. Ohm's law, we need to calculate the current, so I equals V over R. In this case, we know our current is going to be 24 volts. We know that our resistance is only going to be 4 ohms because this 8 ohm resistor is completely shorted out, so it has no effect on the circuit whatsoever. Therefore, 24 volts over 4 ohms is going to be equal to 6 amps, which is our final answer. So just to reiterate, we need to understand the actual behavior of capacitors and how they respond to transient responses, specifically when it's at 0 at time equals 0 in these switching situations, or when it's stretched out fully to infinity. So I'm hoping that you guys were able to understand some of the principles behind circuit diagrams and circuit equations. If you guys want more videos, please be sure to like, comment, and subscribe, and visit us at voltagelearning.com. Until next time, we'll see you guys later.